Okay. Should be okay. All right, so let's see. Any questions on anything? So the on the web page, can everyone hear me?
We can hear you.
Okay, good. And you can see the screen. It's okay. So I changed the let's see. Let me go here. I changed the homework groups a little bit. Hopefully it's okay now. Two people, undergrads, dropped, so that made the this grouping shift up. So it's just two undergrad groups, and they kind of pseudo randomly shift. So hopefully, if those check the numbers and make sure they work. It's like next week, or this week, it'll be like group 2 and group 1, and then it'll be, so I use the old one, so it has like a 3 in it, but there's actually only 2 groups. So it's like group 2 sometimes is 3, and sometimes group 3 is 3. So, and then sometimes there's a group 1. So hopefully you can figure that out, which group you're in. And then the grads had a little problem, but I think I fixed it. So hopefully everything's okay with the numbering in this thing. It's on the web page. That. So, all right, so that's that business. Then I wanted to go through the quiz. I think everyone turned it in. So the first part, I think everybody got this. This should be like negative here because you have, so you're going from amorphous to crystalline, right? And then the enthalpy would drop so it's going to be
camera
negative.
is not showing the paper.
Camera's not showing, thanks. There, all right, so went from amorphous to crystalline, so the enthalpy drives it, so it drops the free energy. So it'd be a negative term. And the entropy should be a positive term. If you're amorphous to crystalline, and the surface energy makes the crystalline less favorable, so it's also going to be positive. So however you write this, the surface term has to be the opposite sign of the enthalpy term. Where I put it here, the same sign, so that should have been negative here. And then this will work out. So you have delta G is B delta H minus T delta S. This should have been minus A times sigma. If you didn't get this, it's okay, but then it's 0, set it to 0. A by V is the thickness, and then S, delta S is delta H by T infinity. So you end up with 1 minus T over T infinity, and then delta H for this thing. And then that equals this other term, sigma. Or there's two surfaces, there's 2 sigma. And then you can solve for the thickness from that. The thickness is 2 sigma over delta H. And if you multiply by T infinity, you get a T infinity like that. All right, so you have this kind of quench depth term here. Anyway, so that's the Hoffman, that's the thermodynamic model for this thing. So I think everyone got that. I glanced at them, but any questions on that thing? Then this business about where do you get the entanglement molecular weight. So I wanted you to see, that's in the PowerPoint. So basically just kind of redo this stuff. So this is a power law fluid, so it's a log viscosity versus log shear rate. You can't read that. And there's a straight line here. So it's a power law fluid. Then it tails over, and this region is Newtonian. So the viscosity doesn't depend on shear rate in this region. So that's this eta 0 number, the 0 shear rate viscosity. It's not always this clean. Like usually this tailover part is buried at the lowest frequency you can measure, so you can't exactly observe this. You need there's a function that will fit this curve that can give that to you. then you can measure this zero shear rate viscosity as a function of molecular weight. So if you plot these, do log viscosity versus log of shear rate, you'll find out that as you change the molecular weight, there's this kind of power law that you could extend back, and then these will like join in like that. So as this is higher molecular weight. Right? So these steps, you could plot this zero shear rate viscosity or log of it, and then versus those molecular weights. So if you go to high shear rate, you'll get the same viscosity. So you only see the difference when you get to low shear rate, because out here, the chains are basically straightened out. So short chains or long chains doesn't matter. The cross-sectional area of the chains is going to be still going to look about the same. So they have the same drag coefficient. But as you lower the shear rate, the chains can relax, and then they become these kind of random walk things. So then the viscosity goes up, and these are entangled. Right? So anyway, so if you plot this, you get a power 1, that the viscosity goes with the molecular weight. Just you add more cars to the train, but it's hard to pull the train. Then you get to the point where they start to entangle, and you have this entanglement molecular weight. So that question was just to you to kind of reiterate this thing, like explain why shear thinning occurs, explain how that's obtained. So I think everybody got that too mostly. Any questions on that, on part B of this thing? And then these things get dicier as you go along. So this one, 7A, shows the confirmation, initial and final. It shows these power laws. So let's see if I have that up here. It's not, that's one of them, not it. So 7A, notice field open. Don't get that. Oops, upside down, close that one. Let's do it. I think this is what I want. Oh, that's the quiz. So I need this one. This is that paper. That's not the right paper. The paper is missing here. We don't need this paper, so let me go back. Need that cost paper. Question C, figure 7A 2399. Oh, I guess it's this paper, right? I'm not cost, the other one. 2399. No, it is cost. 2399. Here. So he shows these three kind of power laws here, right? So so the n it goes with r squared goes with n as the Gaussian chain. That's our NL squared. So you have the r squared goes with NL squared. That's a Gaussian. That's for a Brownian motion chain. That's how the end-to-end distance goes. All right, so it's the average r squared goes to NL
We
squared.
can't see what you're writing.
I'm sorry. Okay, so this equation is just the Gaussian chain equation, right? So he's got plotted r squared versus n, so that would give you the straight line, right? They'd be proportional. R squared is proportional to n, so you get a straight line. The slope of this thing is 1, right? So it's n to the 1 power. So it's not on a log scale. So you can take decades. It's like 10, 100, 1,000, and then 10, 100, 1,000. And if you want a slope of 1, then you're going to go like that. If you want a slope of 2, then you take 2 decades. So you go 2 decades to 1 decade. So this would be a slope of a half, right? And a slope of 2 would be 2 decades here to 1 decade, so like that. Right, so on a log plot, where you have decades demarcated, you just count the decades to get the power. So power 1 would be 1 decade by 1 decade. Power 2 would be 2 decades by 1 decade. Power 1/2 would be 2 decades by 1 decade in the y-axis. Right, so that's kind of how you deal with these plots. Right, so when he gets power 2, that means that r squared goes with n squared. That means r goes with n. So that's ballistic. That means that they're just proportional to each other. Right, so that means the thing is a rod. Ballistic means it's, I mean, in time travel, it would be like a bullet flying, or in spatial, it would be a rod. And that's what you're looking for the crystals, this rod. There's the chains are going to line up in the crystal like that. So, oops. So basically, you're looking for this rod over a certain length up until you get to this kind of thickness of the crystal, and then they won't be a rod anymore. They'll be something else. Probably. So experimentally, they go back to this Gaussian shape. So in other words, you have, it doesn't matter that you have the chains in a crystal, as long as there's randomness to the connection of the crystals, then this chain still has a Gaussian overall shape. So it should go from n small, you'd have r goes with n, and n large, you'd have r goes with n to n r squared goes with n. Right, so expect to see this r squared goes with n behavior at the end of this n2, and you get to the end of the chain. So this kind of has a little divot here where it's going to the end of the crystal, and then it goes back to this Gaussian thing. You can see, so then he has the final confirmation, the chains. So they have this tail over, and then they go to that end here. So this business in here probably has to do with just the transition from the rod within the structure at small scales, and then the connection of these things at large scale forms a random walk again. So that's kind of experimentally verified that you get this random walk on the large scale within a crystalline polymer, and then on a small scale you get this kind of ballistic behavior. And so he's got both regimes, and he throws in this end of the 1/2 thing, right, which is odd. So if you're looking at this, so this thing, you talk about this like in a fractal sense, you say r goes with n to the 1/2, or r to the 2 is n, right? So it's a two-dimensional object. So if you have a disk, then the bigger the disk is, the mass in it goes with the size of the disk squared, because it's going to be the area of this thing, be the mass, and that's the size squared. Right? If you have a rod, then you have r goes with n, so that's one-dimensional. Right? And the other option is kind of three-dimensional, 3D. So if you have a size of a cube, then you cube it to get how many units are in it. So if the cube doubles in size, you get 8 times the mass in it. Right? If a disk doubles in size, you get 4 times the mass, and if a rod doubles in size, you get double the mass. Right? So you have these powers of possibility, 1, 2, 3. Right? And our Gaussian chain is 2, even though it's not a disk. So this could also be this thing. Right? So 1 and 3 only have one answer, like a solid object. And a rod, 2 has several answers. It could be a disk, or it could be a random walk, or it could be some other thing. So this dimensional, this fractal dimension doesn't tell you what the thing is. It only tells you what the mass packing is, what's the density of the thing. So it's not telling you really what it is. So anyway, 1/2 isn't one of those options. This is dimension. When n is 2, because you're plotting r squared, this is dimension 1, and because you're plotting r squared, this is dimension 2. So mass goes with size to the power 2. But in this case, you'd get 4 here. So n would go to the power 4, which is above 3. Right, so 3 is the limit. You can't have anything with a higher dimension than 3 in 3D space. Right, so this idea of n to the 1/2 is kind of bogus. It doesn't make any sense. The thing that makes sense is that he's got these rod structures within the crystal, and they transition to this random walk at large scale. So you have, I mean, I'm not expecting that you get this, but basically this is the story here. That's from my perspective. So you have ballistics. So when n small, you get this ballistic thing because they're within this crystal. And then when you look larger, at larger scale, so this is your small scale view. And then when you look at a larger scale view, you see these things will just be little crystal spots, and your chains between them is doing this walk. This is n goes with r squared. N l squared goes with r squared. And so it's 2D, that's 1D. And this is at large scale, that's a small scale. This is supposed to be an eyeball, by the way, the thing I'm drawing here. But if I put the rest of the guy's head, it would start to look like Homer Simpson or something at some point. Anyway, so that's the story on this thing. Any questions on that? I mean, you could have some other answers. That's kind of what I'm thinking. Some people talked about comparing these two plots. People did a lot of things. So any comments on that? Or so I think there's quite a bit in this question. I mean, hopefully, again, like I'm dumping things on you, and we'll work through this in the class. So we'll kind of figure these things out if you don't get it right now. Then he talks about, let's see, this is a business, there's concentration, so this, I think everyone got that too. So specific viscosity, it's gonna be the viscosity that you measure. So you make a solution, so you have a bucket, you throw your polymer in, and then you're gonna measure the viscosity of that. So you're gonna have your viscometer, sorry. So you have your viscometer, your fluid in here, you're going to spin it, you get the viscosity, right? So, and you're doing it at a slow rate. So that's going to be the stress, the torque that you put on this thing divided by the strain rate, so the speed. Right? So it's kind of like the torque over the speed. It's going to be the viscosity. So the higher the torque you get per given speed, the higher the viscosity, as you spin this thing around at a slow rate, so you're at the plateau. Anyway, so if you plot the viscosity versus concentration for a polymer solution, so usually everything's in a log scale. This has a power law of kind of 3, and then it's going to just go over to the solvent viscosity. Right, so you can't resolve anything at small concentrations because the solvent viscosity is much larger than the kind of the addition that you're adding due to the polymer. So you need to subtract off the solvent viscosity, and then usually you normalize it by the solvent, so you can get this point. So you can get a point of 1 here, which is where this takeoff happens usually. Right? And then below that, you get this adding cars to the train. So you get the viscosity goes with them, just with the concentration. The higher the concentration, the more the cars, the harder it is the torque goes up. And so you have a power 1, you have a power 3. And this would be like 1 decade by 1 decade. This would be like 3 decades by 1 decade. So basically, this transition is where you see like some kind of entanglement concentration, where you start to see the entanglements come into play for the thing. And this is log plots to get these slopes, right? So that's kind of why he's going to the specific viscosity and how you can increase the entanglements with this by adding more chains. So the more chains you add, then the more opportunity there is for chain action, and then you can have those make more entanglements. So the viscosity goes up because you're adding entanglements, basically. Is that okay with everyone? And then, so these things get more and more difficult, I think. So you have this issue that the one theory, that Hoffman thing he did, doesn't have any dependence on entanglements, doesn't have any molecular weight, doesn't have any molecular weight dependence. It's just the enthalpy, entropy, and surface energy. It's just the same as the Gibbs-Thompson equation, which is for like low molecular weight materials. The only difference is that the folds make you have a large surface energy, means that the crystal will be asymmetric. So there's a general rule that for any kind of crystal, like a low molecular weight crystal, that the surface energy by the size for each of the faces of the crystal so the surface energy and size is the equality between all of those things for the different faces of the crystal. So this Hoffman-Lorentz equation, just a restatement of that. You're going to have the size is related to the ratio of size and surface energy is constant for the different surfaces. This has a low surface energy, the fold has high. So that means you get a thin, you have to have a small size for high surface energy in order for this number to be constant. So that the higher the surface energy, the smaller the size. Then this number is just a constant for all the surfaces, right? So anyway, and that constant has to do with the enthalpy of crystallization and this T infinity. So let's see. So Hoffman theory, there's no dependence on entanglement density. So then, so basically the Lou is a kinetic theory and the Hoffman's this equilibrium theory, right? And then the actual situation is going to be like a combination of the two. In favor, oppose the proposition that you can alternative. So in Lou, he doesn't have any attractive potential at all. So his delta H is 0 in Lou. Like he doesn't have an attractive potential. So he wouldn't have, the Hoffman approach wouldn't work. Like he would always get an infinite crystal because it's like sigma. Well, he doesn't have a sigma either. So he has delta H T minus T infinity. So this thing is 0 because he has no attractive potential. So it means his thickness probably is like infinite from a thermodynamic perspective, but he gets a finite thickness in his simulations. Right, so he says that's due to entanglements. Right, so Lou, everything depends on the molecular weight, and in Hoffman, everything depends on the temperature of crystallization. Right, so the two things are different. I mean, there's a number of reasons why it might you have an alternative explanation. It's like you could have just that the kinetics, he hasn't waited long enough for the thing to come to equilibrium. I mean, that's kind of a simple answer to it. And then you can look at Lou's, so always in these simulation papers, they're going to show how they got to equilibrium. So the first thing they'll show is like, how did you reach your equilibrium? I think Lou shows that somewhere. So here he's got dpd steps as time. So it doesn't really look like in a lot of these that he's reached equilibrium, like it's still going up, right, to crystallinity, crystallite size. So if you haven't reached equilibrium, you can't really talk about it that much, right? So basically, equilibrium is always the question you ask for a simulation problem. Right? And people came up with a variety of other answers for that were pretty good. Then the second thing, any questions on that? Or the equilibrium thing is what I was thinking about. And then comment on the distinction between equilibrium thermodynamics and kinetics. And then, so polymers have both kinetic and thermodynamics involved. So some balance between these things is probably necessary to consider these systems. I think that's kind of the main thing here. So that's kind of the quiz. Any comments on that or questions or anything? Hopefully it was okay. I mean, it was a little challenging. It was challenging. There was 3 papers, so it's a lot. So, but basically, I think this week would be a little bit like 1 paper. That's kind of a good thing. But because I actually found the cost paper first, and then I started to use that, and then I found this other paper that referenced it. So I thought that it would be good to put both of them in. And then the Hoffman paper is just a standard reference paper for that, describing crystallization in polymers. In fact, there's a lot more in that Hoffman paper than just this Hoffman-Lorentz equation. It's the whole theory of nucleation is in there, which is kind of messy stuff. Anyway, so that, and kind of put that aside. Then I wanted to move on then, unless there's comments on that. So went through this. I just went through that. This business of viscosity. This is just in the context of what is a polymer, like how do you define a polymer? So we started out, let's see. We started out just saying, well, you can define it as a series of MER units, chemical units, and then from a rheology perspective, it's a behavioral feature. You see normal forces, you see shear thinning. From a kind of thermodynamic perspective, it's got to do with fluctuations in structure. So you get these random walks so that the chain is thermally being moved around to randomize it, and it reaches this equilibrium kind of structure. From a melting point perspective, you end up with this idea that you get a plateau and a melting point as you increase the mass of the chain. Then that's due to chain folding. We talked about that. And then there's this observation of entanglements, right? And then this homework had to do with entanglements and crystallization, two kinds of definitions of what a polymer is. So if you don't see shear thinning, you're below this entanglement molecular weight, it's not a polymer. And if you're above it, it is. Because all of your properties, all of your flow properties, the ability to make a fiber, the ability to make a film, you can only get that when you have these entanglements, right? So only in this high molecular weight polymer region, right? So you can only get any properties out of it out here. If you have alkanes or wax below this and above that, they're polyethylene, right? So that's kind of distinction. And then we started to look at this business. So this is a dynamic viscometer measurement, and you're going to have this ideally a cone and plate setup, right? And I think I showed you some of these, and this is going to be oscillating, right? And the strain is going to be less than 1%. So it's really just vibrating, right? So you have the stress that's going on, which is going to be related to the torque and the area. And then you're going to have the strain rate, which is related to this frequency of the oscillation, right? So basically you're vibrating at acoustic frequencies, and you're getting the stress measurement out of this. You're measuring the stress. So you can plot these two things. You can plot the stress, and it's oscillating, so it's sinusoidal. And then you can plot the strain, right? So the strain might be a different color. I've got a different pen here. So the strain. So they aren't in phase with each other. Okay, there's a lag. This is the strain. And this is the stress, right? And this is 2 pi when you get to here. So this is a phase shift. So the phase angle that goes through that is del. Okay. So you get out of this, if you want to get the viscosity, which is going to be the stress over the strain rate, right? Or you can talk about this in terms of a modulus. So basically, there's kind of two ways to look at this. The measurement is going to be this measurement, but you can convert this. So this thing, because it's got a phase shift, is going to have a real part, and it's going to have an imaginary part. Okay, because it's going to have a phase shift, and the phase difference between these things is going to be this del parameter. Okay, so it's going to be n prime would be in phase, so it's going to be n prime times sine of whatever the phase angle of the thing is, and then it's going to be plus imaginary times cosine of that frequency times this n double prime. Right? So you have this imaginary kind of component that's out of phase and a real component that's in phase. Right? So you're gonna have this kind of breakdown. So of the material, it's only going to have like three parameters that will describe it. One, is from the zero shear rate viscosity, and then this relaxation time. Then we can kind of describe all the properties of the system. Okay, so basically everything's related. So you can rewrite this in terms of modulus. You can rewrite it in terms of compliance. So in other words, if you look at a fixed stress, you stress the thing, and then look at how the strain changes, how it relaxes. So you pull it down and then watch it bounce back. Right. So you put a fixed strain, put a fixed stress on it, and then watch how the thing droops. So you put a weight on it, and then watch strain as a function of time, or you could watch stress as a function of time. Right. So you put a fixed strain on it and then watch it relax. So these kind of relaxation things. If you look at the strain change in time, then you're looking at the compliance. If you look at stress change in time, you're looking at the modulus. And the things, the modulus, the compliance, and the viscosity are all related to each other. We can write equations to relate all these things together. So basically in this, you can get out of this measurement the modulus. And the modulus is going to have a real modulus, an elastic modulus, and this loss modulus, which is like the heat that's given off. But this is like the Newtonian modulus. That's related to the viscosity times the frequency, right? So the typical plot is to go to this modulus plot because that's easier to interpret. Okay, so you do this measurement for viscosity, but you get this modulus plot. Okay, and you're going to plot the storage and the loss modulus against the frequency that you're oscillating this cone at. Right, so the bottom is and it's a log plot because you're going to get power laws out of this. So the power law for storage modulus is 2 when it's in the flow regime. So when you're moving it slowly, it flows. Right? When you move it faster, it resists flow. Because at this point, you can relax the entanglement. So if you're at the low shear rate, then we're in this Newtonian plateau. And then as you get to high shear rate, you get into this power law fluid regime. Right? And in between, this entanglement kind of shear rate, or 1/tau, relaxation time for the thing. So anyway, in this plot of modulus, you see these two power law regimes. One is 2 for the flow, for the modulus, and one is 1 for the loss. And because you're in a fluid regime where it's flowing, the loss part is larger than the storage part. So it's a viscoelastic, but it's flowing, right? When these two cross, that means you've reached this relaxation time, tau, and then the entanglements can't relax. So then they cross because of the steeper slope for the storage than it is for the loss. So they cross there, and it becomes a solid elastic. And you get a plateau modulus. That value of G prime is related to this entanglement molecular weight in KT or RT. So that storage modulus is a way to measure the entanglement molecular weight, this plateau modulus. Meanwhile, this guy drops down, and then if you can get, and this is the extent of a normal rheometer, you can't get measurements beyond that. If you have a special rheometer, this diffusive wave spectrometer, then you can measure on to higher frequency. When you get to that, you find out there's another crossover where it becomes a liquid again. And at that point, you're really looking at really small scales of the chain, where you're looking at smaller scales than the entanglement. So you're starting to see flow again on a local scale. Okay, and the cutoff of that is called the tube diameter. Okay, so basically these curves are complex, and they're interpreted entirely in terms of structural features, even though this is a dynamic measurement, right? So the interesting thing is that all the analysis of this is based on structure. So that this at low frequency, you see flow, then you see the structural feature, the entanglements comes into play that makes it have this rubbery plateau. We'll talk about how you get that value. And then you get to higher frequency where you're looking at small sizes. So a small bill has a high frequency, high pitch, and a large bill has a low frequency. So large things and small things also have to do with time scale. for how things respond to stress. So at this point, you see where, if you think about the entanglements in the system, right, then you can say, well, this chain is going to pass through a bunch of styles, right, where it has to go through a small passage. So it's going to have this kind of pathway that it goes. It's defined by these entanglements, right? And that the diameter of that is associated with this molecular weight between entanglements, right? So that once you get below that size, the chain's flowing within that tube, right? So that's why you see this transition to flow out here. So it's a dynamic measurement. You're measuring dynamics, but it's all structural. All the definition of it is structure. So it's kind of an odd thing. Usually you don't think of structure and flow, but because the flow is causing changes in the structure, then you start defining everything in terms of structure. So this is unique to polymers. So you talk about dynamic measurements in terms of structure. Right? So, anyway, so that's another, and these are some of the, like it's this Maxwell equation that gives you this power 2 and power 1 for viscoelastic fluids. So we can talk about that later on. Anyway, so that's another way to look at defining what a polymer is. Another way to define it is just a structural measurement. Okay, so I have to kind of throw this up at you because you'll see it. So you need to kind of know a little bit about this. So you can take a beam of light, right? Or you can take a beam of X-ray or a beam of neutrons. So neutrons about 10 angstrom wavelength. X-ray is about 5 angstrom. That's tunable. And then light is going to be like 500 nanometers, so 5,000, 5,000 angstrom, right, per red light. So basically, these things are looking at different size scales. The size scale of a polymer chain is going to be about 100 angstrom. So you can see that X-rays and neutrons can probe the internal structure. Light can't really do that because if you write down Bragg's law, so the biggest sign can be is 1, or the smallest, this number can be, sign can go to 1. So the smallest size you can measure is 2 pi over, or 2 lambda, see, lambda by 2. Sorry, there's no pi in this. D is lambda by 2 sine theta, right? So half of lambda, sorry about that. So the biggest theta can go is 1, and then lambda by 2 is the smallest size you can measure. So this wavelength defines the size that you can measure, the smallest size. So 5,000, the smallest size would be 2,500 angstrom, and the chain is 100 angstrom, so you can't really measure the chain with the light. What you can get is just the overall size of the chain, like how big, what's the size of the chain. Right? X-rays and neutron, you can actually measure the internal structure, and this is a neutron scattering for a polymer chain and what you see. So it's the log plot again. So slopes mean something about the structure. Okay, so what is the structure? So the intensity is proportional to the mass of the objects, and mass times the number. So the concentration and the molar mass. And then the Q is basically 2 pi of the size. It's an inverse space vector. So this is how scattering is usually plotted. So you're looking at the mass goes with 1 over size to some power, right? And that the power is a negative power. It's decaying down. And the negative power is 2 means that this thing's a dimension, because we said size and mass goes with this dimension of the object. And we said the dimension for a Gaussian chain is 2. So that's why you get a -2 slope in this thing. That means you have 2-dimensional. As you go to high Q, which is small size, because Q is 2 pi over R, you see a transition to this Kuhn length, the step size. right? And there's a transition point right here. And so you can measure the step size of the chain. You can measure, you can say that's a Gaussian chain. And from this tailover part, you can say how big is the chain. The tailover parts just fit with the Gaussian function. So that ends up giving you the size of the chain. There's a size here, it's a two-dimensional object. There's a size here, and then it's a one-dimensional object. So that's basically our picture of what the kind of what this chain is, right? This idea that you have these steps, and then there's a Gaussian. So you're zooming in originally just at one of these steps. You see that it's a rod, so it's one-dimensional. And you zoom out on Q, and you see that's a random walk. And finally, you see the overall size of the thing. Right, so that's kind of how this technique works. So it looks a lot like the rheology technique where you're looking at power laws. You do log plots, you look at power laws to define this is a flow regime, this is a rubber elasticity regime, another flow regime at high frequency. This is actual direct structural measurement of an object like this. Because again, like if you do that same, and this is a lower, so if you do this simulation, it never looks the same, right? It's the only way to talk about it is statistically to say what that thing is, right? So it's always different every time you do it. So anyway, that's kind of this picture of these different ways to look at and define what a polymer is. If it wasn't a polymer, it wouldn't have this two scaling part. So this Gaussian chain part is necessary to define it as a polymer. Right. So any questions on that stuff? I mean, it's a lot of stuff, but hopefully we can work through it, and then you'll see it over and over. So hopefully it'll seep in, you know. All right. So anyway, so next thing is like this. That was kind of like introduction. Okay. So next thing is to start looking at just kind of the initial part is to look at what the step length is, or look at the random walk first. Okay, so I showed you before this random walk. You can write a program to do it. You start the walk at 0, take a step in a random direction, repeat it n times. Then you get a random walk as long as a random direction that you go in. And so that's kind of this program. You have the 6 possibilities. You can go plus x, minus y, minus y, plus z, minus z. You have a random number generated. You pick one of those. You take that step. And then that makes this walk. This is a 10,000 step chain, which would be kind of typical for a synthetic polymer. Right? And then after that, you can calculate this value for r squared, and it should be proportional to the number of steps that you put in times the step length, which here the step length is 1, so it's just r squared should go with n, right, if you do this right. That only works if you do a lot of chains, like I did 5 chains and I got 5,000 instead of 10,000. But if I do a lot of chains, so if I do like 100 chains, so it's going to make 100 chains, it'll spit out something close to 10,000, that number. Right. Sometimes you happen to hit where it matches, sometimes it doesn't. So you get long chains, short chains. So I got 9,938 with 100 chains. So if I did 1,000 chains, I get exactly 10,000. Right. So it averages out to be this thing. Any one chain doesn't follow this law. Right. So let's see, my camera froze out for some reason. Why? Don't know why. Maybe I should open this again. Oh, the whole thing crashed. This again. This thing should work. If not, it's okay, but is it working now? Yes, right, so that's good. Right, so hopefully you can kind of see where you can get a random walk out of this. I mean, the random walk has some problems that the way I wrote it, the chain can pass through itself. So it's a ghost chain. Right? It can go right through itself because I haven't said you can't do that. So it can do it, right? That's one problem. I have a fixed kind of persistence length in it. So that's another problem. Like how do you decide what that length is? Right. So what is that length? How do you deal with this crossover question? What impact does that have on this chain structure? So there's a few questions, even just within the context of this really simple model, right? So anyway, but still, nonetheless, it you can see that it works. You can see that you get for this particular polymer. This is a polyhydroxybutyrate biodegradable polymer. You can get power 2 here, and then the analysis that you get this plateau is also reliant on a power 2. So you can see that there are cases where you get exactly that kind of situation where it matches up and it doesn't matter that it crosses over. Okay, so sometimes that works, sometimes that doesn't work. And it depends what the condition is. Those are all in a melt state, polymer melt. Okay, so anyway, so you can get this NL squared pretty quickly mathematically. Okay, so you can say that this R squared, average R squared, is going to be the sum of all the steps in the chain, like on 2 points, I and J. And then for their 2 vectors, Ri and Rj, and the dot product gives you this average R squared. So you have your walk. So dot product is a cosine of the angle between 2 steps times R squared, the absolute value for the step. And our step length is 1 here, right? So we're taking our step, we have this R vector, and then there's another R vector. So that's I, this is I plus 1. And we dot product, we find that angle between the two, take the cosine of the angle times that, right? So if this is truly a random walk, right, going in all different directions, this double sum is an average of this cosine. That means that the average of the cosine is going to go to 0 because basically if you take the cosine function, so it's symmetric about 0. So I can go, whatever, this is plus and minus R. So I'm going to have as many that way as that way. So the cosine will average out to 0. Sine doesn't average to 0, cosine would average to 0, right? So basically, because it's a symmetric about 0 function, right? So this dot product, if it's a random system, goes to 0. So it's random for every case except when Ri dot Ri. In that case, cosine of 0 is 1, right? So I can separate this in. So I have this average R squared, right? So it just spits out automatically. If you look at it as a projection of 2 vectors, sum of an average of the projection of 2 vectors, you get this NL squared function comes right out of it, right, immediately. Like you break it into I not equal to J and I equal to J, then you just get that answer. Right, so that should be kind of straightforward. Then once you have that answer, then you can realize if you look at the right papers that this thing is the same idea as a Brownian motion. We have that the Brownian motion of a particle is going to equal the time to the power 1 times the diffusion coefficient. Right, so you have a particle that's wandering around. It can cross its own path, and it just wanders around with time. The average position where it ends up is 0. So the average x squared, the average x is 0, but the average x squared is kind of the sigma of this Gaussian. So you can look at that as if you say the probability at some position x versus x. And you have 0. 0 is the most likely place for it to end up. And it's going to be like a bell-shaped curve around that x. So expect to see exponential minus x squared over 2 sigma squared as a Gaussian distribution function for that position of that particle after it diffuses. Right. So it's the same thing here. These two things are the same problem. Right. Doing this random walk of the thing and doing this Brownian motion are the same problem. So the math is the same. So where did all this come from? Like this diffusion coefficient and all this business. So that came from this paper by Einstein that I wanted to go through. So we already talked about these things. Let's see, this business. Okay, so this 1905 paper by Einstein goes through like where this random walk stuff comes from. So this paper comes up with two things. It comes up with this idea, like defines the diffusion coefficient for Brownian motion. So Brownian motion was observed in the 1800s, right, by a guy named Brown who observed pollen dust particles moving around, right? And it was never explained like why the distance traveled went with the time, travel squared went with the time. So this Einstein paper 1905 was the first thing to describe that. Okay, and also in the process of doing that, he figures out a thing called the Einstein-Stokes equation, which is just intimately tied to the same thing, which we use to get the hydrodynamic radius of polymers and of anything, right? So the Einstein-Stokes equation says that the diffusion coefficient for a particle undergoing Brownian motion is going to be proportional to the temperature, and then it's going to be 6 pi times the viscosity of the fluid times the size of the object, this hydrodynamic radius. So if you can measure the diffusion coefficient, okay, and then you can get this size of the object. So if somehow you can measure the diffusion coefficient, you get the size. That allows you, because you can measure the diffusion coefficient over macroscopic dimensions, the size can be nanometers. So this is a basis for dynamic light scattering. So measuring nano sizes at macroscopic dimensions. Right. And it's also this hydrodynamic radius is also going to be the basis for understanding the flow of polymers. So we'll go through this next time, or maybe not next time, but the time after next time. We'll go through this Einstein's 1905 paper. It's just a couple lines of calculations, so it's not a huge thing. But anyway, I think it's important to do that first, so you have a basis for where some of the things came from. Like where does this Einstein-Stokes equation come from, for instance? And now is probably the best time to go through that. Anyway, so that's about it. We're out of time. So any questions, anything? Did the group thing work out, or was that good or bad? Or Josh, since you're the first guy on the list.
I think it was fine.
Okay. I mean, if there's any problems, let me know, like with the homework and stuff. You can email me. Just email. I mean, I answered mostly. I got like 3 or 4, maybe 5 emails from people, and I answered. And I tried to post it, like email back all the answers as I accumulated a few, so that everyone was in the same boat. And I don't know. I might figure out a better way to do that. But anyway, next week. Oh yeah, next week we're supposed to go to live classes too. Still, so. I'm not sure how to record those. I have to figure out how to do that, or if I can do that. So far, I have that I could set up my cell phone and do it. It's somehow at the back of the room, so I might try that. If anyone has any ideas on that, let me know. So, okay, why don't we call it quits there? I'm over time anyway. So, okay, thanks. I'll see you on Friday. I'll try to post the homework tomorrow too. So.